Welcome back to The Explainer. If you're focused on elevating your problem-solving skills, you are in exactly the right place. Today, we're stepping directly into the high-stakes world of technical interviews by conquering 3 specific, medium-level algorithmic challenges straight from Geeks for Geeks. Think of this as your virtual training ground. We're going to break down the constraints, the complexities, and the core strategies you actually need to master these exact challenges.
Okay, let's dive right into this. Have you ever wondered what unifies the hiring processes at some of the biggest top-tier tech giants in the world? Like, what exactly are Amazon, Microsoft, and Paytm looking for when they bring a candidate into that interview room?
Well, the answer lies right here. These giants, along with Walmart, Flipkart, Adobe, and honestly a whole bunch of others, actively test candidates using the exact algorithmic problems we're analyzing today. When you sit down to solve these, you aren't just coding in a vacuum, right? You are facing the exact same gauntlet that gatekeeps the top engineering roles in the entire industry. The stakes are definitely real.
Now, what's really interesting about this slide is the wild difference in sheer volume. We've got the detect loop and a linked list problem sitting at a massive 525,000 plus submissions. I mean, it's ubiquitous, almost a rite of passage at this point. But then contrast that with the distinct subset sums problem, which has just over 23,000 submissions. It's a much more niche, specialized kind of challenge. Yet both carry that medium difficulty rating, and both are heavily favored by top companies.
So here is our battle plan for the explainer. We'll start with cracking medium-level algorithms, then hit detect linked list loops, distinct subset sums, form largest number, and wrap up with the key takeaways.
All right, Section 1, Boss 1, the infinite loop, focusing on linked lists.
First things first, we need to understand exactly what we're trying to detect here. You're handed the head of a singly linked list. The definition of a loop here is simple, but man, is it lethal. A loop exists if the next pointer of the last node points back to any other node in the list, even itself, rather than just cleanly terminating at a null value. Internally, a 1-based index tracks this connection position, with 0 meaning it properly points to null.
But here's the reality check, guys. This problem has an accuracy rate of just 43.49%. Think about that for a second. Despite being attempted by over 500,000 users, it still trips up more than half of the people who submit a solution. It sounds super simple on paper, but the constraints make it a true medium-level threat.
Those constraints become crystal clear when we look at the expected complexities. To pass this phase of the interview, you absolutely must solve this problem with a time complexity of big O of n. That means you scale linearly with the input size. But even more challenging, your auxiliary space must be big O of 1. You only get constant extra space. There's no way you can just throw a massive hash map at this problem to remember which nodes you've already visited.
So the crucial point is the scale. You could be dealing with anywhere from a single node up to 100,000 nodes. The sheer volume of potential nodes is exactly why that strict big O of 1 space limit is heavily enforced. If you try to use extra memory that scales up with 100,000 nodes, your solution is going to fail the memory constraints of the system. Guaranteed.
Defeating this boss requires a very specific attack plan. Step 1, identify that it's a singly linked list. Step 2, respect that zero-tolerance big O of 1 space constraint. And Step 3, apply what the source tags as the two-pointer algorithm. Basically, by having one pointer move slowly and another move quickly through the list, they're eventually going to collide if a loop exists, all without using any extra memory. It's a really elegant solution to a super common problem.
Moving right along to Section 2, Boss 2, the subset puzzle, dealing with dynamic programming.
Now, the challenge here is distinct subset sums. You're given a set of integers, right? Your task is to find all the unique sum values that can possibly be generated by adding together different combinations or subsets of those given sets. And here's a fun little twist from the problem description. You actually don't need to read or print anything yourself. You just complete the function and return a list containing the distinct sums in increasing order. Simple, right?
Well, much like our first boss, this one is pretty formidable. It holds an accuracy rate of 42.81%. It requires a completely different mental model than pointers and nodes. This one is all about combination, aggregation, and doing it incredibly efficiently. And this brilliantly illustrates the shift in strategy. Just look at these complexities. Both the time complexity and the auxiliary space are exactly the same. Big O of n times sum. The sum here literally represents the total sum of all elements in the array. Your resources scale directly with both the number of items and the maximum possible value they can create together.
So why does that specific complexity matter? Because of these constraints. The array length is capped at 100, and the individual values are also capped at 100. This is a problem explicitly tagged for Flipkart interviews, by the way, and it has a massive dynamic programming focus. That means you'll need to break the problem into smaller subproblems and remember those results. If the constraints were much larger, a big O of n times some solution would totally break the system. But at these specific boundary conditions, it's exactly what the interviewer wants to see.
To conquer this phase, step 1 is recognizing those relatively small array length constraints we just talked about. Step 2 is calculating that maximum possible sum, which is going to dictate your bounds. And step 3 is unleashing your ultimate weapon, dynamic programming. You're building up a table of possible sums iteratively, ensuring you only ever calculate each state once.
All right, Section 3, Boss 3, the concatenation conundrum. Let's talk about sorting.
The task here is called Form the Largest Number. You are handed an array of non-negative integers. Your job is to arrange them so that when you glue them all together, when you concatenate them in order, it creates the absolute largest possible number. But notice the crucial detail here, guys. You absolutely must return the result as a string, not an integer.
Oof! This is our most punishing challenge yet. A 37.82% accuracy rate. This is where so many candidates stumble, because the intuitive answer, just sorting the numbers from highest to lowest, actually fails under some very specific edge cases. The clues on how to solve this are buried right in the expected complexities. An expected time complexity of big O of n log n, that is a massive, flashing neon sign pointing directly to sorting. A standard comparison-based sort operates exactly at n log n time. Meanwhile, the auxiliary space is big O of n, giving us just enough room to maneuver the array.
But you might be wondering, why must the answer be returned as a string? Look at these constraints. You can have an array with up to 100,000 elements, and each of those elements can be a value up to 100,000. If you try to concatenate 100,000 large numbers together, you will instantly exceed the memory limits of standard integer data types in almost any programming language. A string is literally mandatory to hold a number this massive.
Let's move to the strategy and see how this builds. Step 1 is identifying those massive integer constraints so you don't accidentally break your data types. Step 2 is recognizing the need for that string concatenation. And step 3, the real secret to defeating this boss, is utilizing a custom sorting algorithm. You don't just sort by size, you sort based on which concatenation order forms a larger string. For example, you're comparing string A plus string B versus string B plus string A. That's the real game changer here.
So, what does this all mean as we wrap up? What's the big takeaway from running this gauntlet? Honestly, these 3 problems are practically an entire curriculum on their own. To survive them, you have to demonstrate a true mastery of fundamental data structures, the optimization techniques of dynamic programming, and the clever implementation of custom sorting. Tech giants aren't just looking for code that works, they're looking for code that respects strict constraints and runs incredibly efficiently. You now have the exact blueprints to tackle 3 of the most notorious medium-level problems on Geeks for Geeks. You know what Amazon, Microsoft, and Flipkart are actually looking for, and you know the constraints you have to beat. So I leave you with this question. Which algorithmic boss will you challenge first? Get out there, fire up your development environment, and start practicing. Thanks so much for joining me on this explainer, and keep learning.